In this question, you are again asked what is the minimum length of a mirror that is required for you to see the full picture. And it's a similar question to a previous question in the worksheet. And the shortcut method, if you have watched my previous video, the shortcut method doesn't work here. And that's the reason why in the previous video I said it's good to learn the proper method, because the technique to solving this is always the same. So please watch the earlier video and watch this video, and you will realize that it's actually the same method. So the answer to this question is 4 meters, and we have to construct ray diagram to locate where the image is. We will draw some ray diagram later on, and finally, for this type of question, we will need to use similar triangles to do some calculations. So let's start by using the object distance equals to image distance. And I realized that the object distance is 20 meters. That's the dimension of the room. And therefore, with this, the image can be located. The height of the image is 12 meters because the object and the picture is 12 meters long. So with that, I will now try to draw the light ray that allows the man to see the full picture, the full image. So you can see now two gray lines, two gray dotted lines that are drawn, and this shows how the man sees the image, because light travels in a straight line. So with this, we will realize that we actually need this part of the mirror, this small part of the mirror, and that will be the minimum length that we are aiming to find. If the mirror is shorter than this minimum length, then we are not able to get any reflection, and that's why we can't see the full image. So this is the dimension, the length that we are looking out for in our answer, and the answer to this question is 4 meters, as you will realize later on. Okay, so moving on, I have now drawn in the light rays in red, and you can see that in front of the mirror, this is a real light ray, so I use a solid line and an arrowhead, and that this is a reflected ray, and I can easily join the incident ray by starting from the edge of the picture and connecting it to this point where the reflection takes place. So I do it for both ends of the picture. And once I've done this, we will notice that there is two triangles that you can see. So this is triangle, I label it triangle B, the very big triangle, and there's also triangle A. So these two triangles are similar triangles, and the rule for similar triangles learned in math is that the ratio of the sides is always the same. So we'll just use that in a calculation. So the height of A, which is over here from this part to the base of the triangle A, that's the height. So if this height divided by the height of triangle B, which is from the man all the way to the base of the triangle over here, is 10 meters divided by 30 meters. I can get the height of triangle B to be 30 meters because over here, this part is 10 meters, half the room dimension, and over here, the long side here is 20 meters because that's the image distance. So we have gotten the ratio 1/3, and then we just equate it to the base of A over base of B, because the ratio of the sides is always the same. So once we have done that, we notice that the base of triangle B is 12 meters, and we can easily solve for the base of triangle A, which is 4 meters.